Hello students, in today's class we will read about dielectrics and polarization. So first of all, as the topic says, we need to read about dielectrics. What are these dielectrics? These are known as the non-conducting substances. Non-conducting substances. Any substance which have property of not conducting can be said as a dielectric. Then why we are reading this topic of dielectric under the topic of electrostatics? What is the need of understanding something which is not conducting electricity? So this is an important topic with respect to capacitors. Plays a very important role in making a capacitor more efficient, and we will see in the upcoming section how it is used in the capacitor to make it more efficient. The second thing we will read is the polarization. Polarization is a phenomena basically, and the phenomena in which we aim at making something polarized. Making something polarized. Polarized implies just segregating their positive charge and their negative charge. We are trying to segregate it. So why we are doing polarization here, we will understand this concept. For what we are doing polarization is the second concept we are going to see, and how it is important for the substance we are looking at the topic of polarization, how it is important. These are the three factors. Along with these three, the fourth thing we will look is that how we are making a substance polarized, how we are polarizing. So what we are going to see is why polarizing, what polarizing, how polarizing, and how it is important to be polarized for the given substance under the topic of capacitors. Okay, so we'll get started. Dielectrics are the non-conducting substances. They do not conduct any electricity, and the difference between a dielectric and conductor is as seen. Conductor is able to conduct, whereas dielectric do not have a property of conducting. Okay, now in these dielectrics we will look how these dielectrics are getting polarized and how these dielectrics are important, because the dielectrics have a property of getting polarized. These are important. If this dielectric says that I am not going to get polarized, then it is of no use. So where these dielectric and conductor have similarities in getting the polarized, but how they are getting polarized is different. How a conductor polarizes and how a dielectric polarizes is different. So we will see how this is the difference. So coming up to the diagram, kindly pay attention to the diagram over here. See, in this given electric field, this is the externally provided electric field to this conductor and to this dielectric. To this conductor and to this dielectric we are providing external electric field, that is E naught, and we will see how the this externally provided electric field is playing a role in the conductor, in the dielectric. Both the roles are little different. Electric field provided is same, and this electric field have strength equal. They will try to do the same thing in the conductor as well as in dielectric, but there is a phenomenon difference in conductor and dielectrics because of their difference in the property. Now this is external electric field. When this external electric field is applied in the conductor, these free electrons and free ions, basically we will not say just electrons, but it can be a proton or it can be a neutron and it can be a electron. So we will aim at speaking it as the free ions present in the metal or in the conductor starts to form an internal electric field. They get segregated and they will have this internal electric field in the opposite direction. Internal E opposing externally, E external. Okay, so these are free ions. Which plays a important role are free ions. So these free ions start to form opposing internal electric field. So this internal electric field and external electric field both are opposite but equal, So these two cancels out each other, giving us a sum of 0, so there isn't any electric field present inside the conductor. This thing we have seen in the previous section when we were reading about the properties of conductor under potential, electric field, electric forces and all these things. So this is what we have seen, that inside the conductor electric field is 0, and today we are understanding why it is 0, how this is justifiable. Now see the case of dielectric, the second case. Same external field is provided and same ions we are having inside. But these dielectrics have two types of ions in it. One are the polar ions or the polar molecules which made up this dielectric, and other are the non-polar molecules which make these dielectric. So according to these polar and non-polar, we are defining this diagram in general. There is in this particular diagram we haven't taken any polar molecule or any non-polar molecule. We have taken a general dielectric where we can justify both for polar as well as for non-polars. So see, we have this surface charge density sigma p due to the polarization happening due to external electric field, and surface charge density which is its original, dielectric's original. So this external electric field provided will aim at these the conductor the ions over here inside are producing some sort of uh, internal electric field also, that is EIN, that is inside of the dielectric, which is the electric field produced. But in this case the E inside produced by the inside ions or these polar molecule or non-polar molecule is either small to the external one or it is greater than the external one. It possibly is, can be greater, can be smaller, but is never equal. Okay, so mostly it cannot be greater because here this is a induced field. Anything which is induced will never be greater than the original one. So we eradicate this idea that this internal field can be greater. So what is the only possible is that the inside field, which is a induced field, is smaller than the external field provided. Hence when they add up, when these two add up, EI, like E in plus E naught add up, then what exactly happens is that it is not equal to 0. It is not equal to 0. So see over here, I'll just change the pen. See over here, E naught plus E in is not equal to 0. Is not equal to 0. So there is some sort of electric field left. In case of dielectrics, there is the remnant of electric field, but in case of conductors there is no such remnant of electric field. These induced or the inside electric field cancels out the external electric field which is being provided by us. So this is the difference between a conductor and between a dielectric. And this one property of dielectric, that not all the charge is being like not all the electric field is being eradicated in this case, will help us in making it efficiently a combination with our capacitors. Okay, but the same capacitor cannot be kept with a conductor, because here no electric field inside, but here there is existence of electric field inside the dielectric, existence of electric field inside the dielectric. Okay, so this is one of the main differences. Now we will read basically conductors. First we will understand conductors as I have already explained. Then we will go to dielectric, and in dielectric we will learn two different cases. What are the two different cases? One is the polar case and one is the dipolar case. Okay, so see the point number 2. In contrast to conductors, they have no or negligible number of charge carriers. In the presence of external electric field, what happens to conductor is explained over here. Free charge carriers move, and charge distribution in the conductor adjusts itself in such a way that electric field due to the induced charges opposes the external field within the conductor. These induced charges, the charges which are being induced due to this external electric field, get their own internal fields, and these fields will start opposing the external field. This happens until in the static situation the two fields cancels each other and the net electrostatic field in the conductor is zero. So this happens up to a point where E internal is equal to E external in case of conductors. So these two cancels out at this point, these two cancels out, and the electric field overall becomes zero. But in case of dielectrics, see over here, we are talking about now about dielectrics. Free movement of charges is not possible, as we have seen they have, in contrast to conductors, they have no or negligible number of charge carriers. As they have very less number of charge carriers, they do not provide any free movement of our charges. So when there is no free movement of charges, what will happen? The external fields will not be equal to the internal fields. Internally, they will not be able to produce enough fields. It turns out that the external field induces dipole moment by stretching or reorienting the molecule of the dielectrics. In dielectrics, they are composed of molecules, and these molecules are being stretched like molecules, and these are stretched like this is one molecule. Both plus and minus are here. Now we provided electric field, this will get little stretched. So this charge will get segregated as plus ion and then minus ion. This will create little polarization. So every molecule in this dielectric will get polarized. Once every molecule will get polarized, the polarization will sum up and will give a huge polarization. For a single one, it will be very small, very negligible, which is of no use, but as a whole, many molecules get polarized will give us the needed polarization sum. Now, collective effect of all molecular dipole moments is net charge on the surface of the dielectric, which produces a field that opposes the external field. So this overall dipole, when all these polarization add up, it becomes a big molecule which is being polarized. So what happens basically when it is a polarized, anything which gets segregated as a minus q and plus q, it forms basically a dipole. Okay, so in under the condition of dipole, they will have their own electric fields, and that electric field opposes the external electric field. Unlike in a conductor, like in conductor, this doesn't happen. Okay, however, the opposing fields so induced does not exactly cancel the external electric fields, it only reduces it. What basically is happening, these internal fields are small enough from the external electric field that they do not cancel each other. They do not cancel each other, but reduction of reduction of external electric field is done. In conductor, what happens? Electric field inside the conductor is 0. E inside equals to 0. But in this case, E inside is not 0. So this is the justification that why conductors do not have electric field inside it but on surfaces, and this is again a justification how these dielectrics are more important and useful in this case than the conductor. Now see, extent of effect depends on the nature of dielectric, how much the electric field will be reduced. It depends upon the dielectric, not on the provided electric field. Provided electric field will remain same no matter what, but if our molecules in the dielectric have the property of getting more polarized, then they will reduce more the external electric field. But if they have less ability to get polarized, they will do less reduction of this electric field, the outside electric field. The molecules of a substance may be polar or non-polar already. Till now, we were in general looking for a dielectric molecule. Now, what they have introduced to us is that in dielectric there are two types of molecule. One is polar molecule, another one is non-polar molecule. Non-polar molecules are the neutral molecules. They do not have the segregation of plus or minus. Their centers coincide. Like this is a negative ion, its center is over here, and this is again, I'll make with a blue ink, this is again a positive ion and its center also lies over here. So both positive and negative coincides. So see, there is no segregation, there is no fighting between the positive and the negative. Both are sitting on a same chair or a same sofa, adjusting very well, right? But what happens in the case of polar molecule? Polar molecules are like friendly people, but they do not agree at every term. They stay together, friends, they stay together but have different centers, friends and enemies. They are like friend and enemies. How is it happening? Is that like there is a positive charge over here and it is little segregated to the negative charge. So they have this difference of some 2A between them. They will show some dipolic properties. They already are little stretched out, little polarized. So in the case when we are providing electric field to them, both these polar and non-polar behaves little differently, behaves little differently in presence of E, in presence of E or the electric field. See now, in non-polar molecules, we will first see about the non-polar molecules. Center of positive and negative charges coincide. Already explained. The molecules then has no permanent or intrinsic dipole movement. It's not molecule, it's movement. Okay. Now we will see in case of non-polar molecule, we have reading about non-polar molecule. They do not have intrinsic dipole moment, and example is oxygen, hydrogen. See O2, one O, other O, and H2, one H, other H. Okay, because of their symmetry, they have no dipole moment. They are symmetrical. Most of non-polar molecules are symmetrical. Symmetric geometry. Now we will see how does a polar molecule different from a non-polar molecule. A polar molecule is one which the centers of positive and negative charges are separated even when there is no external field. So from here we can conclude, if we provide E external to non-polar molecules, we can see polarization happening. Okay. In case we are providing external electric field to non-polar molecules, we can see polarization happening. But in polar molecule, charges are already separated and they have intrinsic polarization already, intrinsic dipole moment existing already. So in case we are providing external electric field, what will happen? That we will see in the upcoming lines. Okay. They have a permanent dipole moment. They have permanent dipole moment. I'll write over here permanent dipole moment. In case of which type of dielectric molecules? In the polar molecule, polar type of molecules, and these do not have permanent dipole moment. Permanent dipole moment. Okay. Example for the polar molecule is HCl and water, H2O. See our diagram. A non-polar hydrogen molecule, a non-polar carbon dioxide molecule, but a polar HCl where Cl, chlorine, is negatively charged and a bigger atom than the hydrogen which is positively charged. In H2O water, what is HCl? It is hydrochloric acid. Hydrochloric acid. And see over here water, this is a negative charged ion O, this is positive and this is positive. Due to this have some positive density and this have negative density. They are moving little apart. So they have created dipole already. Already they are bit polarized. Now when we are providing external field, external electric field, what happens in the case of polar and non-polar? We will see now. In external electric field, positive and negative charges of non-polar molecule are displaced in opposite direction. Displacement stops when the external force on the constituent charges of the molecule is balanced with the restoring forces. So what happens? Restoring force. This is our positive charge, this is our negative charge. Both are having same center. Now, same center. We provided E external and they are segregated. They will keep on segregating up to a point where the external electric field is balanced by the, I'll write over here, restoring force from dipole. From this dipole, they will start stretching up, but they will have some restoring force also, as every dipole have. So this restoring force will be like normalized with external electric field. So after that, this stretching will stop. These positive and negative ions or the charges will stop moving more apart. So that will be the exactly length of dipole. Okay, this will inhibit excess length. So it will only get stretched up until unless this restoring forces are being balanced with the given external electric field. So this is what happens to our non-polar molecules. See over here, the non-polar molecules thus develop a induced dipole moment. They develop a induced dipole moment, but polar molecule already have dipole moment. Non-polar induces dipole moment, but polar molecules have already gotten polar moment. This is a very much important line, a very much important statement, should be noted by every one of you. Why is it important? Because this is a characteristic which defines a non-polar and a polar molecule, and this is defining as well as differentiating property. Both these have this as a differentiating property, so both have little difference in their principle of working. Okay, defining property, defining as well as differentiating property. Of dielectric molecules. The dielectric is said to be polarized by the external field. In this case, this dielectric is said to be polarized by external fields. Come to the given diagram over here. See, this is our non-polar molecule. These are having the coinciding centers. These are not stretched apart in the absence of electric field, when there is no external electric field provided. Now we provided electric field. What happened? These positive and negative charges are stretched apart but in opposite direction to E, opposite to E, opposite to E. So now we can see that electric field is coming in this direction. Here is the positive and here is the negative. So they got segregated in the opposite to E direction, and every charge is got polarized. Each and every charge present in a non-polar molecule gets polarized. So such substances where we get 100% of efficiency are called linear isotropic dielectric. Linear isotropic dielectric substances for which assumption that when the induced dipole moment is in the direction of field and is proportional to the field strength. First thing, this induced dipole is in the direction of given field, induced dipole moment in direction of the field and is proportional to the field strength, is proportional to the strength of the electric field applied externally. Induced dipole moments of different molecules add up, giving a net dipole moment of dielectric in the presence of external field. So every molecule will have a induced dipole moment. Each and every molecule's induced dipole moment will add up to give us what? To give us the total dipolic moment of our dielectric substance, which makes it more heavier, okay, which gives more strength of dielectric polarization. A dielectric with polar molecule also develops a net dipole moment in the external field, but that is quite different phenomenically. In the absence of any external field, when there is no external field, different permanent dipoles are oriented randomly due to thermal agitation. So, the total dipole moment is 0. So what exactly happens? Total dipole moment is 0. These are randomly assigned here and there, randomly arranged. Why randomly arranged? Because here this positive and this negative will start getting, but this positive and this positive will start repelling each other. So they have these thermal agitations. To avoid this thermal agitation and internal attraction and repulsion things, they are randomly organized. This random organization gives us the dipole moment, total dipole moment equals to 0. Total dipole equals to 0. So when we provide external field, see, this is the case for E equals to 0. This is going here, this is going here, this is going in this direction, in this. But see, in the case of when there is E provided, when E is provided, this is going in this direction, in this direction. So everyone is going basically in this direction from here to here. So they, in the presence of electric field, these randomly organized molecules start to get oriented with respect to the given electric field. When an external field is applied, the individual dipole moment tends to align with the field, When summed over all the molecules, there is then a net dipole moment in the direction of external field, that is, the dielectric is polarized. Now, in the case we have seen in these non-polars, what we have seen is that these get polarized in the opposite direction to electric field. opposite to E. But these non-polar molecules what they exactly do is they get polarized, but along the external provided field, along the external electric field, they tend to align this, and this makes the dielectric polarized. Dielectric then gets polarized. So what is the difference between the non-polar and the polar? The only difference which we have seen over here is in non-polar there is no polarity, there is no differentiation of polarity. But in the case of our non-polar, in the case of our polar, they are already having polarized moment, but as they are arranged randomly, their overall dipole moment is 0. Now we provided external field to non-polar, they will start segregating and will get polarized, hence making dielectric polarized. And then we provide external electric field to non-polar molecule, and once we provide dielectric field to polar molecule, these polar molecule which are already stretched and are random get aligned and oriented in the direction of electric field, and this makes the dielectric polarized. So phenomena of getting a polar and a non-polar dielectric get polarized is little different, but at the end of the story we are getting a polarized dielectric. The extent of polarization depends upon the relative strength of two mutually opposite factors. Extent of polarization. The dipole potential energy in the external field tending to align the dipoles with the field, and thermal energy tending to disrupt the alignment. Thermal energy is the energy which is between these two charges as the attraction of the opposite charges and as the repulsion of the same charges. So this extent of polarization, how much a dielectric will get polarized depends upon external electric field provided, potential of dielectric to get polarized, and these intermolecular attraction and repulsions, intramolecular attractions and repulsions. So these are the few factors at which polarization of a dielectric media depends. In addition, there may be the induced dipole moment effect as for non-polar molecule, but generally the alignment effect is more important for polar molecule. So this is again an important statement. For our non-polar, it is the induced dipole moment. What we are doing with external electric field is we are inducing the dipole moment, but with respect to our polar molecule, alignment of these molecule is important. They are already having a dipole moment, but what they do not have is the discipline they don't have. They are not aligned and well oriented. So what basically we do is we tend to align them by providing the external field, and we will get a net dipole moment and a polarized dielectric. Thus in either case, whether polar or non-polar, the dielectric develops a net dipole moment in the presence of an external field. So at the end of all this story, the moral we get is the dielectric develops a net dipole moment, and that happens in the presence of external field. This development of a dipole moment does not happen in conductors. The dipole moment per unit volume is called polarization. So I will write over here what is polarization again. Please make a note of it. Polarization, dipole moment per unit volume. Per unit volume. Make one note of this, because this is a very straightforward statement kind of definition for polarization of dielectric, and is very much important with respect to your entrance as well as board exams, because this is a simplest explanation. It does not contain big statements and big sentences and formula. Just a simple line: dipole moment per unit volume is polarization of dielectric. It is denoted by P with a head arrow. So our polarization is a vector quantity. Vector quantity. Now for linear isotropic dielectric, we have read in the previous slide what is linear isotropic dielectric is something which have like properties of getting polarized properly and efficiently. So this dipole moment P in terms of polarization is given as P equals to epsilon naught chi e e head arrow. So this symbol is chi, is a Greek word. It is pronounced as chi. Ch is k, in I is I. Okay, so this is chi. Chi e is a constant characteristic of dielectric susceptibility of the dielectric media, electric susceptibility of dielectric media. Now we have got a question under this section, is that how does the polarized dielectric modify the original external field inside it? What exactly happens to the external field, the original external field, when these dielectric get polarized? Like, why are we reading polarization? Why are we reading dielectric? We are reading because they make some changes, they modify external field. To modify the external field, we need to know the polarizing property of a dielectric molecules. Once we know this property, it is very much helpful for us to choose the shape and sizes, to what extent we want to modify our external electric fields. So this question is very nice question and should be answered very confidently, and let's get to the solution. How is this question a justifiable question, a justifiable statement? Now let us consider a rectangular electric slab. We are considering a rectangular electric slab. Okay, it is placed in a uniform external electric field. It is placed in a uniform external electric field. Uniformity is always needed to get proper calculation, and this is the slab we have placed. Okay, and this electric field is parallel to two faces. To this face it will be parallel, to this face it will be parallel. Okay, parallel to two of its faces. The field causes a uniform polarization P of dielectric. So as the field is uniform and our dielectric is uniform, everything is uniform, what happens? They will start uniformly polarizing. This will happen. Uniform polarization will happen. Thus, every volume element del V of the slab has a dipole moment rho del V in the medium of field. One molecule, how much of dipole moment they will have? P bar. And then one molecule, not mole, then the whole system containing these molecule, X molecules, will have how much? This is equals to Y. y equals to xp. So here x is not any number, but this x is considered to be the volume. So what we will get, p into the volume, p into the volume. For the given volume we are defining the dipole moment. The volume element del V is macroscopically small but contains a very large number of molecular dipoles. Of course, molecule is small. Molecule is small and containing a quite vast number of molecules in macroscopically small volume. Just I'll give you a little example. If you are out of the earth in this space, the earth will look like a small football ball or maybe a basketball. Okay, if you will go far, it may look like a cricket ball, later on a tennis ball. So it as far you will move from the earth, the size of earth will start reducing. You will see a smaller version of earth. So this small earth contains many millions, maybe trillions of humans in it, right? Trillions of humans are on the earth. But when you go far away, are you able to see these many men on the earth? No, you cannot. Similarly, for us, this world of molecule is very small. But this small world of molecule contains too much of small ions and smaller molecules in a given defined volume. So this volume may be macroscopically small but have a very large number of molecules in it. So we'll have a good quantity of electric dipole moment. Now see, anywhere inside the dielectric, the volume element del V has no net charge, because see, this and this will get combined, this and this will get combined, this and this will get combined. Combined doesn't mean they will get smudged up with each other, but it means they are nearer to each other. They are near to each other will show attraction. So this charge will cancel this charge, this will cancel this. So these positive charges will cancel out these negative charges. These positive charges will cancel out these negative charges. These positive charge will cancel out these negative charges. So what is left? These charges are left out charges, and in this corner these charges are left out charges. Okay, so inside here in this particular area there is no charge content. Okay, no charge dipole, no charge, no dipole. Okay, but like this surface will have a net of charge, will have net charge. Why? This charge is contributed from these charges which are not being cancelled out, because there is no charges available to cancel out these. So surfaces have some charge density. A dielectric surface have charge density. Dielectric surface have charge density on surface, but not inside. But then what is inside? Inside we have dipole. Inside dielectric dipole persists. Okay, dipole exists. Dipole persists. Now see, this is because the positive charge of one dipole sits close to the negative charge of the adjacent dipole. As I have already told, these two are the dipoles, positive, negative, positive, negative. This distance is more than this distance. Distance between the dipole is more than the adjacent dipoles. Okay, so these will cancel out their effect. At the surface, the dielectric normal to the electric field, there is evidently a net charge density because these does not get cancelled out with any other charge. From the figure, positive ends of the dipole remains unneutralized at the right surfaces and negative ends at the left surfaces. We have already learnt and explained the figure. The unbalanced charges are the induced charges due to the external field. So these unbalanced charges, these are not balanced. Something which is not neutralized are called unbalanced charges, and these are the induced charges due to the external field. These charges are said to be induced charges due to external field. Thus, polarized dielectric is equivalent to two charged surfaces with induced surface charges of sigma p minus sigma p. Sigma p is polarized surface charge, minus is due to the minus. This deals with negative charges, negative charges. No other significance of minus here. As it deals with the negative polarity, it is negative sigma. The field produced by these surface charges opposes the external field. So whatever field these charges are producing, these charges which are under the influence of electric field and are known as induced charges, opposes the external field. So these induced charges, I will write over here, induced charges tends to oppose provided E external. The total field in the dielectric is thereby reduced from the case when no dielectric is present. Surface charge density plus or minus sigma p arises from bound, not free charges in the dielectric. This is again one of the big difference in dielectric. Bound charges play important role. But in case of metals, they have free charges. Free charges are present in the case of metals. So now we need to understand how it is important to place a dielectric in a capacitor. Okay. See, we have seen a dielectric which will get polarized. When we are polarizing dielectric, we found that dielectric is of two types, non-polar and polar. So we will leave dielectric over here. We will see over here conductors. Conductors, we provided E external electric field. This induced E internal. As induction happened in the free charges, the induction of electric field was equal to electric field of external. So no E inside the conductor. So this is the story of conductor. Now dielectric get polarized. While polarizing, we found non-polar and polar, and this polarization is happening to bound molecules, bound molecule, not to the unbound. In non-polar, we will find that no initial dipole moment, but in polar we have a dipole moment already exist. Now we provided E external provided. What happens now is that this get induced polarized, induced dipole moment. Dipole moment already exists, but random existence, hence no dipole. Now this happens over here, and what happens? External field is provided, randomly arranged, get oriented. I will write molecules, polar molecules, polar molecules get oriented alone E external, hence dipole moment. Okay, so here induction is important and here alignment is important. I'll write over here alignment. Alignment is important. Here induced dipole moment is important. Now next we aim to find is that as these are giving induced or the alignment, in both the cases provided external field is always greater than the electric field which is produced inside due to these dipole moments. So they have some leftover electric field. Now we have a parallel plate capacitor. This is parallel plate capacitor. Parallel plate capacitor. Now if there is no, we have got the two cases, no dielectric and another case is that we have a dielectric. Present. Okay, when there is no dielectric, the E produced, electric field produced between them remains as big as it is produced, remains same as big as it is produced. Now in the case of presence of dielectric, E produced reduces as per the property of dielectric introduced between two capacitor plate. Okay, so when dielectric is there, this electric field get reduced, but when there is no dielectric present, this electric field remains same. Hence, to modify electric field, to reduce electric field, we introduce a dielectric, and hence we need to understand the polarizing properties, because how much we want to modify our electric field. According to that, we have to take a non-polar or a polar molecule, or highly polared molecule or a highly non-polar molecule, as per to requirement of the strength and magnitude. Okay, so this is how and why we are reading polarization in dielectric. Here in this concept, we have understood why conductors do not have electric field lines inside it too. So it is a very interesting topic as well as a very fruitful topic. Hope you understood, and in the last this slide I have summarized each and every point in the very short. So maybe this flow chart is more understanding than the written up concepts, and maybe more helpful. So go through it once again, study it, understand it. This covers up most of the basic concepts and properties of conductors also. So this is the basics. From here we will start reading about capacitors and how electric field is modified in capacitors, how the charge voltages are modified, how the capacitance is modified. So from this particular class, the basics of all this is starting up. So just go through the whole content very properly, understand each and every point to get a better view of the upcoming classes. So that's all for today's class. We'll meet up in the next class with another new interesting topic. Have a very good day. Bye bye.